in this video we're going to be dealing with a rotameter. So a rotameter is a ball inside a cylindrical tube, and so in this rotameter there's going to be 3 different velocities because there's going to be a fluid going in through the bottom of the rotameter, and this is going to be at position 1, and so there's going to be a velocity here, and then as the fluid flows through in between the cylinder and the ball, that's going to be position 2, and there's a velocity there, and then once it leaves the space between the ball and the side of the tube, it goes to position 3 as it continues to flow, and that's going to be velocity 3. And this ball has a diameter d0, and there is a pressure at each of these positions in addition to the velocity. And so we can assume that there is the ball is at steady state. And so at steady state, it's not moving up, it's not falling down, it's sitting in the tube. And so at steady state, the acceleration is going to be equal to 0. And so it's important that we establish that the acceleration is equal to 0, because what this allows us to do is to balance forces. And so the 2 forces that we can balance is the effective weight of the ball and the pressure forces within the tube. So because the density of the ball is heavier than the density of the fluid, we have to account for this. So the density of the ball minus the density of the fluid times, it'll be the volume of the ball, so that's going to be pi times the diameter cubed divided by 6, and that's going to multiply by the gravitational acceleration. So this is going to give us the effective weight force of the ball, and so that's going to balance out with the pressure forces. So that's going to be the pressure at position 1 minus the pressure at position 3, that's the initial and the ending position. That's going to be multiplied by the cross-sectional area, so that's going to be pi times the diameter squared divided by 4, and so this is going to be the pressure forces, and these balance out because the acceleration is equal to 0. And so now we have to determine what is pressure 3. Well, the pressure at position 3, if we look at the pressure at position 1, it goes from a very small cross-sectional area to a very large cross-sectional area. And so when it goes from small area to a large area, there is a sudden expansion. And this is important because with a sudden expansion, there is no pressure recovery. So with no pressure recovery, that means that at the small area, pressure at position 2 is going to be equal to the large area pressure at position 3. So we can plug that in for pressure 3, we can plug in pressure 2. And so if we were to isolate pressure 1 minus pressure 2, we're going to multiply by 4 over pi times the diameter squared, because that's the reciprocal of this term here, and that will allow us to bring it to the other side. So we'll have the density of the ball minus the density of the fluid times the 2 pi's will cancel out, leaving us with 2/3 times the density, or not the density, excuse me, the diameter times the gravitational acceleration. And so that is our balanced forces equation. And so this is important because what we want to do is we can then move on to Bernoulli's equation, which will allow us to relate pressure and velocity, which will ultimately lead us to the flow rate. And so Bernoulli's equation is the pressure at position 2 minus the pressure at position 1 divided by the density plus velocity at position 2 squared minus velocity at position 1 squared divided by 2 plus the gravitational acceleration times the height at position 2 minus the height at position 1 is equal to frictional heating. But for this equation, we're going to assume that the height difference is so small that it is equal to 0, and that frictional heating is also equal to 0. So that leaves us with these two terms here. Set equal to 0. So what is velocity at position 1? Well, we know that the flow rate at position 1 is going to be equal to the flow rate at position 2. And so flow rate is just defined as velocity times area. So using that knowledge and plugging in here, we know that velocity at position 1 times area at position 1 is going to equal the velocity at position 2 times the cross-sectional area at position 2. Simplifying for velocity at position 1, we have velocity at position 1 is equal to velocity at position 2 times cross-sectional area at position 2 divided by the cross-sectional area at position 1. So we can actually plug this in to this equation here. So we'll have pressure at position 2 minus pressure at position 1 divided by the density plus velocity at position 2 squared minus this term here. So we'll have velocity at position 2 times the cross-sectional area at position 2 divided by the cross-sectional area at position 1 squared divided by 2 is equal to 0. So we can actually bring the square inside, squaring the velocity at position 2, area at position 2, and area at position 1. And then this will allow us to distribute out the velocity at position 2, giving us the pressure at position 2 minus pressure at position 1 divided by the density, plus velocity at position 2 squared divided by 2 times 1 minus area at position 2 squared divided by cross-sectional area at position 1 squared. This is equal to 0. So if we look here, we can see that the cross-sectional area at position 2 is very small. And so if the cross-sectional area at position 2 is a very small number, when you square a very small number, it gives you an even smaller number. So with this, we can assume that the cross-sectional area at position 2 squared is going to be equal to 0, and 0 over any number is going to be 0. So this would make this term equal to 0. So 1 minus 0 is just going to be 1. So that's going to leave us with pressure at position 2 minus pressure at position 1 over the density plus velocity at position 2 squared divided by 2 is equal to 0. So again, we want the velocity isolated because once we isolate velocity, we can use it to calculate the flow rate. And so if we were to isolate velocity at position 2 squared, we'll have velocity at position 2 squared equals, to bring this term to the other side, we can either make it negative or we can switch the pressure. So it'll be pressure at position 1 minus pressure at position 2 instead of pressure at position 2 minus pressure at position 1 divided by the density. And then we'll multiply this entire quantity by 2. And so we still have that squared. So we're going to take the square root of the entire term. So that's going to be velocity at position 2 is equal to the square root of 2 times the quantity of pressure at position 1 minus pressure at position 2 divided by the density. And this is why we have this balanced forces up here, because now we can plug this equation in for the pressure at position 1 minus pressure at position 2. So we're going to have the velocity at position 2 is equal to the square root of 2 times the quantity of this equation here, so that's going to be the density of the ball minus the density of the fluid times 2 times the density, or 2 times the diameter times the gravitational acceleration divided by 3. And it's going to be this entire quantity over the density of the fluid. And so now we have the velocity at position 2 established, and so we can then use this to find the flow rate, which again, flow rate is just velocity times area. But an important thing to notice is this velocity, this tube here is perfectly straight. It's not tapered, it's not anything, it's parallel. And so what this means is there's only one velocity that will work for where the ball will be in equilibrium, because anything greater than that velocity, the ball will shoot at the top. Anything less than that velocity, the ball will sink to the bottom. And that's not what we're looking for, because with a rotameter, we want to use the height of the ball to determine and calculate the flow rate. So rotameters are actually not perfectly straight as drawn here. They're actually slightly tapered. And so this illustration is kind of an exaggeration so you can see the taper, but actual rotameters have a very small taper, so you can barely even see that it's tapered. But so there's a taper with the ball inside. So depending on what height the ball is at, you could actually calculate the flow rate of the fluid that's going into the rotameter. And so the diameter there's the initial diameter, and then the diameter is changing with the height. So we'll have the initial diameter d0, and then the new diameter of whatever the height of the ball is. And so we need the diameter as a function of the height. And so we can actually establish that this is the height. And so what we can use to relate the diameter to the height is slope. So diameter is just going to be the initial diameter plus the slope m times the height. And so this is important because if we were to actually talk about flow rate, so flow rate is velocity times the area. So it would be the velocity. Because the area is always changing, it's going to be pi times the diameter, so the height of whatever the ball is at, or the diameter of wherever the ball is at, divided by 4. It would be squared. And then it's going to be minus the pi times the initial diameter squared minus 4. So that is actually the area that we're working with because of the taper. And so as we defined here, diameter is just the initial diameter plus the slope times the height, because again we want diameter as a function of the height. And so if we were to plug this equation in for diameter here, we would have the flow rate equals the velocity times, we can distribute out pi over 4. So it would be times the initial diameter plus the slope times the height, that quantity squared, minus the initial diameter squared. So if we were to square the diameter here, we would have the velocity times pi over 4 times the initial diameter squared plus 2 times the slope times the height plus the slope squared times the height squared minus the initial diameter squared. So the initial diameters can subtract and cancel out, and so that's going to give us the velocity times pi over 4. Again, I drew the taper very exaggerated here, but the taper is actually very small, so the slope is actually a very small number. So when you square, again, a small number, you get an even smaller number, which is the same logic that we used here with the cross-sectional area at position 2. And so this slope here, because it's getting squared, we can assume that it's going to be 0. So we'll be left with 2 times the slope times the height plus nothing, just 2 times the slope times the height. And then so this velocity here is actually going to be this velocity, position 2. And so if we were to plug in all of the equations we have, we would have the flow rate of a rotameter is the velocity, which is this constant here. So that's going to be the quantity of 2 times the density of the ball minus the density of the fluid times 2 times the initial diameter times the gravitational acceleration divided by the 3 times the density of the fluid. And so we can actually multiply this 2 here into the equation. So 2 times 2 is going to give us 4. So we'll have 4 in the numerator. So it'll be that quantity, it'll be the square root, so to the 1/2, and then multiplied by the pi over 4 times the, so this pi here and this 2 here will actually cancel out, so we'll have pi over 2 times the slope times the height. And so that is our equation for the flow rate. Small correction to this equation is when you distribute or square this equation here, this will actually be 2 times the initial diameter times the slope times the height. And so all that's going to do is add in the diameter here and then add it into our final equation here. And so that is our final equation for the flow rate.